Okay, so can you hear me? Hello? You can see the font? Can you? If you can't, you'll have to come close. I can't change this right now. So if you can't see this, you should come close. This is one of the most important slides. So okay, uh, so I have been working on some prototypes in past few months, and so we had to use some technologies there, Akka streams we used, and as a part of that we learned a lot of things, especially about streaming, in general streaming things, right? And I also try to connect dots from learnings using Scala collections or Spark and stuff like that. And I also try to compare how things work in different libraries like say C# or Clojure and stuff like that, right? Reactive streams is very specific. It's about a protocol, but that's not very important. We'll discover that as we go, right? So I have been using Scala for a long time. It's like 4 years. I've been coding in Scala, and Scala collections. People who like Scala collections, and they are used extensively, right? I mean, they are the main strength of the language. Uh, but Scala collections are in-memory collections, and I hope all of you understand the implications. But this is just to make it clear that if you had a pipeline of data processing where you are reading from a source and then doing some processing like say squaring each number that you read, and then you have to do some other step which is take only two of them and then do some terminal action which is called sync, but doesn't matter whatever it is, right? Then what happens at each stage there is a in-memory collection which is created, and then you can see that this is really bad if my source is big, right? The first step itself will go out of memory and nothing will happen. So each of the blocks are representing in-memory collections, and they may get garbage collected very efficiently if you're not holding pointer to that, but that will not work for the I/O programming because of the in-memory thing, right? But before we move on, I must say that this kind of collections work very well for the small data processing steps, which is 90% of the data, 90% of the data transformation tasks which typical business applications do. So I'm not very eager to just switch to a lazy collection or a push-based systems that I will cover now for doing my usual application stuff. I will stick with in memory because there is some beauty to that. It's very easy to reason about, and that can be explained with the second part, right? So the second part is a graph. So now what I have done, after reading, I'm doing two operations. One is a square and one is a double, and then I do further processing. I take one, take two, blah blah. But if you have used Scala collections, you wouldn't even think about this twice, right? You would just use it, and it will just graphs will be created. Why? Because everything is immutable, so they can be easily shared, and they are in memory. So you don't. I mean, the cost is upfront known. You know that okay, each step is going to bring some data in memory, and then it will be garbage collected. But this becomes very tricky the moment your collections are not in memory; they are lazy, and we'll see how and why, right? But you appreciate this point, and just to illustrate the downside of this part, I'm going to run a small demo, and then there are many demos to follow. The demo will try to depict the same stuff, but let's see if you can read it. So here, the project. Okay. So I have created a branch. I have created a graph actually. I'm forking after reading, and then I'm saying that a square, and then say take 5, and then take 10, and then for each. And in the end, for each doesn't do anything. It's a dummy sync. It will just basically consume items and not do anything. Now here square, double, and such, right? I mean they are dummy stages. They square, but that is not important. What is important is that they log. So if you go to square, I'm using it for logging, right? So is it visible, or should I make the background white? Good, right? So this is mainly for logging, right? And then let's see how it works. So now if I run the test, Even though I'm expecting to work only on the 5 elements in the first branch and 10 elements on the second branch, I don't really have much control. So if I run this, what will happen is my data source had a lot of numbers, 20, right? Well, reading for all the 20 will happen. After that, squaring will start, and it will happen for all the 20, and then doubling will happen for all the 20, right? And you are seeing the side effects. You are not seeing the actual end result, but just side effects. But that is what we care about right now. So which means that I can't short circuit, even though I'm interested in the only 5 elements of my huge file. I have to basically get everything in memory and processing. That is obvious, but just wanted to highlight. Okay, any questions on the eager pipelines before we move on? So the lazy pipelines, right? So lazy pipelines come in many flavors, and then let's explore one of them, which is a pull-based pipeline. People will define it in different way, but let's try to visualize the same steps that we look for eager. But here we say that it is a stream. So which means that my sink will determine when I need the next item. So instead of things being pushed this way, things are being pulled from right. Okay, that is the difference. And what is the factor which does the pulling? Well, it's a call. It's some call basically to upstream. It's some call to the upstream. And that call is typically a iterator, next call on the iterator. That is how the most pull-based systems, including, we'll see the examples later, is implemented. And then this next will not return unless it has done its job, right? Because it has to return your value. And well, inside that, there will be a call to upstream next, and it will not return unless it has done its job, and so on till it goes to the source. And then the values will start coming out. So first, next call will come back with the value 1, because I had 3 values. So it will come back with the value 1. It will pass through the stages. Square will not change it. Take 2 will allow it to pass, and I get it here, right? And then the next call will terminate. So this next call will return after all the steps have been done, right? So pull has happened at all the steps. You understand that? And we are imagining now that we are on the same process, but it need not be same process. It could be across the processes. It could be distributed system like Spark. But this is what it will be, right? You will always pull. And which means that because it's a lazy system, the right side is pulling the data. It can short circuit. It can say that, you know what, I want only 2 elements. So it will get 1, and then it will get 4 after squaring, and then nothing happens. So how big is the file doesn't matter, right? This will just work. So this is the basic minimum style of data processing if you want to deal with IO or large files. But there is a downside. Can anyone say what is the downside here? It's blocking, right? Which means that if you are doing very IO intensive programming, you have to make use of threads so that you can do things in parallel. I mean, you can argue that all these calls I will fire in parallel, but then each one of that call will consume a thread, even though, and then you'll be your bottleneck threads will become your bottleneck, right? So you have to allocate literally thousands of threads. So that is not really preferred in the IO world. That has other side effects also, but will not go there. So that is a pull-based model. Well, push-based model is opposite of that, and then now you can guess, right? It's a dual. So Eric Meyer calls it a dual of a pull-based model, and a dual in all dimensions. So instead of right side pulling it, the left side will push it, right, to the downstream. So source somehow magically will start pushing to the first step downstream, and then that step will push to the next, and that is the basic premise. Well, but when will it do that? I mean, there are 2 steps. First, I still define my pipeline as if I'm defining it for the pull-based or in-memory collection. So I say source.read.map.take.for each. But till I attach this sink, nothing happens, right? So that is called as a blueprint. So when you create a lazy pipeline, either pull-based or push-based, when you define your operations but don't attach a sink, nothing happens till that point. It's just a blueprint. It's just like it's a record of your intentions, which is staged and stored. The moment you attach a sync, work starts, and that is what we saw here, right? If I don't attach a sync, nothing will happen, but sync will now trigger in a pull-based fashion. Similarly, for the push to start, you need to attach a sync. As soon as you attach a sync, the source will start pushing the data downstream. That is how the majority of the push-based systems work. There are variety which we'll see later on, which don't follow that. Second important point is that instead of calling next on the iterator, right, you call on next of the downstream and push data on next. So on next is a carrier of your event, and you say that, okay, I have an event of a new item in my source, and you basically push it using on next and pass it in that callback, and that is obtained by the next step. Right? What is important here is this black. I mean, I don't know if you can read it. It's buffer basically, right? So the whole premise that it's possible to have this push-based system can theoretically make it very scalable, because now there is no bottleneck, there is no blocking. Each stage can work at its own rate. For example, if source is producing faster, it is allowed to. So because it's a push-based system, it will, as it gets the data, it will start pushing to the destination, which is the next step, and destination will work at its own step and push the data to the next step, and this will go on. But to be able to do that, you need a buffer, right? So if there is no buffer, what will happen? You call on next, and within that on next, if someone is calling the next on next, and so on, well, it is as good as blocking. You complicate the design, but you don't gain anything, because you know what? It's still blocking. Even though it's push based, it's blocking because you are. It's a bad practice to do anything in the event loop, and you are blocking the event loop. You are saying on next, and in that you are calling someone's on next, and you don't know. Maybe the last step here, sync, is basically a really blocking call in the UI, right? Which is rendering something, and then the whole pipeline will be blocked. So that is not the intention of the push-based systems. So buffer is very important. As soon as you get an on next, you need to just buffer the element and return the call, right? So that I can fire n number of on next calls to this stage at my own speed, and this guy can do the same, right? But the basic mechanism of short circuiting and filtering and mapping will work as expected. Right? Well, there is a problem with this design also. What is the problem? Can anyone? Right. So now you have to control the buffer, right? So you have to have finite size of buffer, and then you have finite size of memory, and then unless that buffer is your disk, this will run out of memory. So you need to do something about it, right? So there are many attempts to do that. The simplest attempt, which RxJava did, and now they're changing. Have you heard of RxJava, by the way? How many of you? Okay. So RxJava is a Java, and now also available in RxJS, and it's a way of reactive extension. Well, you should do a blocking operation in the sync, right? So for each print line, you print line basically, and that's a blocking operation. So well, that will give back pressure. So basically, it's as good as a pull-based system. So there is no problem of buffer overflow, because I'm not allowing the call to return. Right? That's cheating actually, because then doesn't matter whether the only advantage in that case is, well, you can still deal with infinite streams, which you can't deal with pull-based system, but that is a small advantage. That is not what we are looking at. Any questions on this part? This comparison of pull and push? No, right? Well, infinite things are working at their own pace, basically, right? So they started even before you connect. So where will you pull from? Infinite sources actually give you data. They don't. Right. If you maintain a buffer which is dropping, so if Twitter maintains a buffer which is dropping, from that buffer you can say next, and then yes, you can implement that, but that will not be very meaningful to implement a pull-based systems on an infinite stream, because anyway the data will be dropped, and that is not very useful, I would say.
Or the source will have to maintain the buffer.
Yes, someone will have to maintain the buffer somewhere, and then the similar problems will occur. So there won't be much difference. I mean, both the ways, whether you use pull-based or push-based, if you if you don't follow the basic principles like buffering at each stage, you will create back pressure somewhere, and that back pressure will be blocking, and you will be back to supporting the scalability using threads. You can do that, but that is not very desirable. No one does that. I haven't seen, I mean, in practice, people using pull-based systems to do that. Okay, so now there is a third approach, which is the approach that I'm going to use in my libraries, and that is the hybrid approach. Well, there is an overlap. It's kind of a mix of the two. If you see here, right, it looks very similar to the push based, but there is an arrow which goes on in the other direction, like the next, right? But the name of that arrow is, instead of next, it is called as request. And what does it do? That each of the downstream will demand, it's a demand signal. It will demand n number of items from upstream. And upstream will have to respect the contract that it will not push more than n. So it can push up to n, but not more than n. And each stage will be smart enough to know what is the total buffer allowed, what is the current size of the buffer, what are my watermarks, how well I am historically I am doing, and then can tune the demand. Can say that, okay, no, I'm overwhelmed, I don't ask for more. And if you don't ask for more, you will not get the data back. Now, what is the difference between next and request then? Well, in request, you can pass your demand, which is not just one element, but many elements, but that is not the main reason. The thing is that it's a dotted line, right? And then, which signifies that it's an asynchronous demand, right? This is a fire and forget call. So like this dotted line which comes on the right, which is a fire and forget call, ideally if you don't block, demand also is a fire and forget. So you say that each stage just signals a request call based on the current status of the buffer, and then the upstream says that, oh well, the downstream doesn't want more, so I will not ask more from my upstream, and so on. So this demand or back pressure, in other words, gets propagated all the way up. And if source is capable of understanding that back pressure, which is the case in many use cases that I'm going to show you, it will slow down. It will slow if it is that kind of a source. There is a name for that, but we'll see that later. And this is basically a combination of both. And for this protocol to work, it is required that all the connections understand this protocol. For example, only 3 stages of the pipeline understand that. Well, you are back to square one. I mean, it's like what the interface between the 3rd stage and the 4th stage will be problematic. So that's why many people have come together across the communities, and they have created a protocol called the reactive streams. How many of you heard of reactive streams? Yeah. Okay, so you can just search for reactive streams, and there is a page there. So TypeScript guys are involved, Scala guys are involved, of course, Akka team, but Oracle is involved, and RX Java guys are involved, and Dudley is involved. Many people. So there is a hope that it's a set of 4 interfaces and 9 methods, and it's a Java-based protocol, and the hope is that it will become the standard and be included in the JDK 9 as an interface. That is where things are going. But it's not an API really. It's an SPI, service programming interface. Which, for example, if you are building a library which should support back pressure, you should follow that protocol so that you can interoperate between, say, Akka streams and RX Java and Reactor and so on. So that is about that. So I'll just briefly summarize. So pull-based systems are synchronous because of the next iterator-based call. The blocking, and blocking acts as a natural back pressure, so you don't have to worry about it. On the other hand, push-based systems are asynchronous. They are non-blocking. They're high throughput, supposedly, but slow downstream will cause the buffer overflow. And there's a fine print that, well, you can avoid that by blocking, but then that is like not consistent with the objective. And the hybrid is a mix of both. And it's preferred for the IO programming. At least I prefer that. And there's another terminology called hot and cold. Well, that is the difference between the 2 streams. One stream which is capable of slowing down or not starting. So initially we said that unless I attach a sink, the source will not emit the events. But that is not true. For example, Twitter is another example. So if you connect to Twitter API, which is streaming API, Well, Twitter is not going to hold on its events basically till you connect or till someone connects, right? It's going to drop the event. So it's a hot stream because it is started emitting even before a single subscriber has joined. Well, Twitter is one example, but the most common examples of these is UI programming. So, for example, if you want to model your mouse clicks or mouse moves, right, or button clicks or any UI event, right? Well, I mean, there is no beginning and there is no end, right? It's like, of course, there are infinite events, but they don't wait for the first subscriber to join. So until that point, they can't prevent user from clicking, right? So those are called hot sources, that sources which emit data even in the absence of a sync. Okay. But all the other cases which are very interesting for IO programming and data transfer, they are cold sources where they can, for example, if a huge file lying on the disk, or a web service which is being called across the TCP network. Because TCP protocol itself understands the back pressure, and then if I'm hopping from one machine to the other machine, but over HTTP or any TCP based communication, I'll get the back pressure, and the end system, if it is database or a file, will get a back pressure and will not throw the data at me. So those are the two terminologies, and after this I have one. I'll go to graph. But so far, is any question so far? Okay. Well, in the beginning I said that, you know what, the in-memory collections are really nice to work with because you never think of graphs and all that. The cost model is really simple. Now here it is not in the lazy systems, either pull or push. It's not that simple. So what we are doing here is we are so in the first case, right? In the first case, I'm reading twice. So I have a fork. I have to do square and I have to do double. So I said, well, I will just read twice, right? And then do the stuff, which is nice, which is very predictable, like as predictable as in memory collections. Nothing can go wrong. But you know what? In-memory collections can turn out to be much more efficient in this case. Depends on what is the cost of read. For example, the cost of read is the maximum in the whole pipeline. You are paying that cost twice here, right? For in-memory collection, it will always be once because you just read it and get it in memory and then pass that immutable collection to two branches, right? You appreciate that, right? That you so in the languages or in the libraries where this is the default, right? You should be aware that, okay, when you're passing your immutable lazy data structures across functions, right? What is the possible cost that you're paying? So it's not as simple as lazy streams being better, right? You have to appreciate that. Well, you can try to overcome that, but then that becomes complicated. So that you can overcome by either memoizing, or in the push-based system, it's called multicasting, that you read once or you do upstream once, and then you can allow multiple downstreams to make use of that data. And there are different ways to do that. But if I am able to do that, then that will be really nice, because then if read is an expensive operation, I'll be able to I'll be paying that cost only once, right? So that is, and we are going to see the actual runs and understand this. Okay, let's do that. There are various ways to memoize, which is like cache the data for lazy streams and multicast, and let's try to explore some of them in the code. Any questions? So let's start with the pull-based systems, the simple systems, right? Well, I have the same model, right? I have 20 numbers, and then I'm going to fork them and want to do something with the 5 in the first branch and something with the 10, which is doubling the 10 elements. And now I'm classifying these collections into either perishable or reusable, right? So let me not call them collections, these pipelines. Perishable pipelines are similar to iterators, right? Or Javaite streams that they can be used only once. And then you can see the implication. Now, Scala iterators, if they are used once in the forking style, so what I'm doing is I'm getting these numbers, getting the iterator, and then doing a read operation. And after read operation, I pass it to the fork, which does the branching, right? So, but I'm working on an iterator. So let's see what is the behavior. Okay, so what happens here is I'm reading 1 to 5 and then squaring them, right, as expected. But my doubling starts from the number 6 because it's a perishable collection. I haven't done any effort to memoize or multicast. So data is going to get lost, right? So first 5 elements will get opportunity to be squared, and the next 10 elements will get opportunity to be doubled, right? And that is expected because the nature of the stream is perishable, right? But I can memoize it. I can say that you keep the intermediate data structure in memory, and there are various ways to do that. Now, this need not be a full memoization, which means that after I have read elements, get everything in memory. It need not be like that. It could be smart. It could be incremental. That okay. For example, if downstream, right, all my subscribers, if they are not going to use more than 20 elements, then there is no point me getting all the data in memory, even in the multicast scenario. So I want that opportunity to be preserved, and that is what the incremental memoization. If you're using Scala, then Scala streams, which people use a lot for doing Project Euler kind of problems, they work in a similar fashion. So what I do here is I have my iterator, right? I read it, but before passing, right? Before passing, sorry, this is the second one is the first one. Cached. Okay, so what I do is cache it using two-stream method. So two-stream will convert this iterator into stream, but at that point it will not come in memory. It will come in memory as the data is flowing through it, and it will retain it. It will not discard unless all the subscriber there are no pointers to that stream, and then it will get garbage collected. So if I do that, then how does it behave? Well, so I get 1 to 5, and they are squared, and then 1 to 5 also get opportunity to be doubled, right? So you see that doubling is happening from 1 to 5, and then there is no more element left in memory because the first stream was only about 5 elements. Then it starts reading from the 6th element. So I prevent duplicate reading of the first 5 elements, but I still continue reading the next elements, right? Why? Because the sum part was saved in memory, right? And that was because of the streaming nature. And that is where the memoization part comes in. It doesn't discard it. It keeps it till all the pointers are collected. And there are, depending on which library you're using, there could be more optimal solution. Now there's a danger with this kind of a model that, you know what, you never know how big, how greedy, how demanding the downstream is. And if they want all the data, then all the data will come in memory at that stage, right? At the multicast stage, which is you're back to square one, right? I mean, it's like as good as in memory collections. In memory collection, at least your cost model will upfront. When you do I/O, you would know that, oh, this is going to come in memory, so either you provision or don't do it. Here you will be like very happy for when you're developing, when you deploy, and then one fine day you realize that, okay, well, no, it's not working as expected. So that is another point, that lazy operations, I mean, they're very beautiful and seductive, but there is a hidden cost. You should understand that. So Scala also has a duplicate method on iterator, which will create 2 iterators pointing to the same source, but it will keep only the delta in the memory. Which means if there are 3 iterators, one is consuming very fast and it has consumed 10 elements, the other has consumed only 5 elements, then only the delta, which is 5 elements, right, will be kept in memory, which is slightly more efficient, but yeah, I think it's just well, reusable streams. Again, going back to the same diagram that we had, but in this case now not an iterator but a reusable stream. They're slightly better, but only slightly. For example, in the simple case, which I lost first 5 elements per iterator, here I will not lose it because it's a reusable. What is the example of reusable stream? Well, in Scala world, they're called views. They're called views, and then you can convert any collection to views and do that. So here you see that, okay, you read 1 to 5, right? And then you square 1 to 5. You don't lose any data because doubling also starts from 1 to 10. And the downside is that it's being read twice. The 1, 2, 3, 4, everything is being read twice, and that is because you haven't done the multicasting yet. It's a simple model, right? So what can we do here? Well, you can apply the same strategy that you applied earlier. I'm just going to run one of these. memoize, right? The moment you memoize, there is hardly any difference whether it is the source was perishable or not, right? And you get the same result. 1 to 5 are squared, and then 1 to 10 are squared, but 1 to 5 are not read again for 1 to 10 are doubled, but 1 to 5 are not read again. Only 6 onwards is being read, right? So this is about the pull based systems which are perishable and non-perishable. Any questions so far? Please.
You said the iterator is duplicated, right? So I have say 3 iterators are attached to the same source, and everything that is being read is kept in the memory. Then who is to clean up the path? The data that has been read by all the iterators needs to be cleaned up, right? Is it left to the cabling or is it?
No, the library implementation will do that. Library implementation will if you go to in the duplicate method source code, you will see that okay, they keep some buffer, and usually for in-memory collections, which iterator is pointing to, this will never be the case. But if it is really there is an imbalance between the speed, then only the delta of that will be kept in memory. Unlike a stream will just memorize everything basically as it goes. There is no opportunity to basically discard some elements, right? I'm not sure. So streaming way is very common. I have a slide where I actually name the libraries. But streaming is very common way of programming in Clojure, for example, right? So all the operations are like that. I'm sure they will be smart enough, and then they will try to discard some of the items and not memorize everything. But I'm not aware. I mean, I haven't read that. Does it?
Yes. So when the library tries to cleaning up, then what about the performance? Previously, we're just waiting. Now you have to keep track of what was said and when to release that.
Well, performance-wise, it may not be. Depends on the implementation. It may not be. Depends. You can see. I mean, I'm just giving examples of some implementations. Usually, the iterator-based implementations are pretty good. I mean, very good in performance. All the Scala collections internally use iterators. So I would prefer that rather than streams if I were in that situation. But I will not use either, and I will use push-based systems.
Comparing with Scala views, Scala views generally stack the modification functions and then apply all those functions together when the consumer is called.
That's right.
So, but to mimic the streams functionality, what if I use a lazy val inside each of those functions, so that those will be computed only once. Even in the case what you told, the 1 to 5 will be computed only once if I use a lazy val, because that will be emergency. So that will be equivalent to streams.
So lazy val is about a reference, right? Many of these lazy data structures internally use lazy vals. They do use lazy vals. But if you think in terms of a data structure and a collection of items, then that concern is orthogonal. I mean, whichever way you do it, what are your options? Either you read twice, or you keep somewhere, and that somewhere is in memory, right? So that is the option, whichever way you do that. With the views also, we are just converting views into streams and getting that functionality. But if there is other way possible, that is fine. I mean, there will be yet another method of the library, but essentially principle will remain the same.
But the only difference I see is I don't require a blocking push-based downstream pipeline or views. I consume as and whenever I need it, which is equivalent to streams, but without.
Well, no. The moment you have a pull-based system, you are blocking. Because the characteristic function of a pull-based system is a next call, right? And the signature of next gives you a T back, which is a blocking call by design, right? It cannot return unless the T is materialized and available, which means inside that someone will call the next, and inside that, so by design, so there is the problem. Now what you can say is that, okay, no, I will fire all the next calls parallelly as much as, but then that's a different way of scaling. It doesn't work. It doesn't work for IO programming. Okay, so this is about now let's go to the push-based systems. So equivalent to the perishable and reusable, the terminology here is hot and cold. So hot is somewhat similar to perishable, that okay, it's streaming data even before you connect, and cold is similar to the reusable, right? And then if the hot source, I can multicast both of them, but if I don't multicast the hot source, then some systems will not even allow me to add more than one subscriber. and I'm trying to add more than one subscriber. So I convert a number stream. Now this number stream is interesting. I create numbers 1 to 10, right? And then I don't know. No, sorry, it's not 1 to 10. Infinite numbers, right? So if you see these numbers, they're created from iterated from 1, which is 1 to infinity, and then I emit them every 50 milliseconds, right? So it's a throttle. I say that throttle element because otherwise I won't be able to demo you anything. So I say that okay, emit. I have a source which is emitting numbers, monotonically increasing numbers every 50 milliseconds, and then I do a read operation on them basically here itself, right? Before I come, and then I fork it. But before I fork it, I make it hot. I mean, because this depends on the library, but somehow I make it hot, and then I fork it. Now fork is also interesting. Fork is making use of two flows. One is a squaring flow and one is a doubling flow, and then they are working at a different speed. Now this is a push-based system, so I have to bring in the time element to show you how things work. And then the squaring flow is being throttled at 200 milliseconds, and the other one is at 100 milliseconds. So both of them are slower than the source upstream, but one is more slow than the other, right? That is the simulation that we're trying. But then in the end, I just do the fork. I have two pipelines basically, right? Two branches, and that's it. And then I connect them. The connection part we'll see later, right? Okay, so if I run this, I'm supposed to get error because that is how the library has chosen to implement it. I'm using, but others may not throw an error and will allow to connect the other subscriber at a time. So it allows only one subscription because it's a unicast. So I'm able to read elements basically, right? I'm able to square the elements. I'm able to square the first some 20 elements. So last element that I square is 36. And why is that? Because the source is hot and source is push based, which means that there will be drop of data, and that is what we are simulating. So we are saying that reading lines here are representing the speed of the source, which is 50 milliseconds. So I'm reading 4 items, and then I am squaring the first one because squaring is paced at 200 milliseconds. And then what happens to 1, 2, and 3? Well, they are dropped. They're dropped. That's how the library implements it. I mean, you can't do much about the hot sources, right? And then the next opportunity is to square of number 4. What happens to the in between? I mean, they are dropped, right? So you get the picture that every few elements will be dropped and few elements will be squared. And then there is no opportunity for anyone to double because the library doesn't allow it. But I can multicast it and say that okay, allow multiple subscriptions. This will work, but then again with the drop of data, 5 numbers will be doubled, 10 numbers will be squared, but they won't be the first 5 or first 10. There will be some right, whichever the library gets opportunity to do. So now squaring is happening on 1, 2, 5, and so on, and doubling is happening on the last squaring goes till 33 and last doubling goes till 15 or so. But you see that both the operations, because the source is hot, there is a data drop. Okay. Well, if I now go to the cold systems with a unicast, you will see that the things will happen properly as expected. First 5 numbers and first 10 numbers, but they will be read twice because there is no multicasting. Okay. So reading 1 and reading 1. So 1 is read twice, but squaring happens to 1, 2, 3, 4, and 5. Right? Yeah, this is the 5. And then doubling also happens to 1, and then it goes all the way, and then final. Okay, squaring happens till 10, sorry, and doubling happens till 5. That is, sorry, I get mixed up with the numbers. But the first 5 and the first 10 both get the opportunity to be squared and doubled. Right? So that is about the unicast. But if I multicast it, in that also I have 2 flavors. Now in the push-based systems, I said that if source is cold and you connect a sink, the data starts flowing, right? But now I have 2 branches. So there are 2 sinks which are going to connect. Now the challenge is that okay, maybe these things will connect at different point in time, right? And there is no way for the source to know that how many subscribers are going to subscribe in future. So there will still be some data loss. It won't be first 5 elements and first 10 elements. Why? Because I'm connecting in the fork. If you see, I'm connecting the two graphs at different points. So this is graph.run is the first branch which is being connected, which is being started. Sync is connected, and then graph2.run is the second one. And there is thread.sleep, the 500 millisecond gap between the two. So there is a data loss, and we want to see that. So if I go back, well, squaring starts, but then doubling starts only at 5. So there are first 4 elements are lost because the second stream takes time to attach, right? So this is not ideal. I mean, even the source was cold, I was able to back pressure it, but because I attached 2 subscribers at different time, there is a data loss. I can prevent that by doing a single trigger basically, right, for the entire graph. And for that, I have to have some way, some DSL or some API basically to do that. Now this example is specific to Akka streams, but there is an equivalent of this in RX also. What we do here is we access is our source basically, right? And then we have a broadcast element. It's a junction. So access inputs to broadcast, and broadcast has 2 ports, output ports. One goes to the squaring flow, one goes to the doubling flow, and the whole thing is defined as a single graph. This is a single graph. And then I connect the graph at one point and get 2 futures back. So this is a single connection. The run there is a single run, so single trigger. Now this should be the best thing to do. So here, if I now go and run this, you will see that there is no data loss, right? So reading happens only once. So if you just want to verify, reading 1, 2, 3, 4, 5, 6, 7 till 12 because of buffering. And then if you say doubling happens only 5, the first 5, and then squaring, it happens 1 to 10, right? So there is absolutely no data loss. And even though my source is faster, it is 50 milliseconds than my downstreams, right? It is being back pressured because after all it's an iterator, right? It's iterator which is being slowed down by the throttle, so it can be further slowed down by the back pressure, and that is a demo of the back pressure. So I think this is like we are 90% done. This is one UI related demo I want to do, but before that, let me see if there's anything in the slides. Oh well, this is just a summary actually. Let's do the summary and then we'll take the questions. So I think we discussed different memoization approaches. There I have put some names. So view to list. This is a full memoization. You shouldn't do that. IEnumerable also does 2 list, it seems, which is in C#. If you have IEnumerable, it's a lazy API. But once you have to fork it, the only recommended way is make it into in-memory and then fork it. In the RDD Spark streaming, right? The data structure is RDD. Well, it has the same problem as the lazy data structure. It is a pull-based data structure. It is not push-based because internet uses iterator. And then in case of RDD especially, the doing the read twice or doing the upstream, which could be expensive operation twice across the network is a big deal. So they have specifically talked about the whole Spark is about basically ability to cache. So this cache is roughly equivalent to 2 lists of these libraries, which actually gets that stage in memory. What I'm not sure about whether it does in one full way or whether it does in incremental way that as and with the opportunity to short circuit. I'm not clear maybe, but that's a small point. Scala streams are the automatic way of doing it, and closure sequences also are like that. In my opinion, this is a bit risky way to do it. Program always against automatic memoized sequences. And the minimal is just one library example. For multicast, your options for the cold stream is really back pressure. I mean, you should be able to say upstream that okay, slow down. But if upstream is not cold and you can't back pressure, then the options are basically drop. So some element, either the hottest, the first or the last or the whole buffer will get dropped, or you can fail the stream if you want. And this is like all whatever I articulated. I mean, this is in this slide that okay, you can talk of lazy pipelines. Eager pipelines we just ruled out. Lazy pipelines of two types: the pull-based and push-based. Pull-based pipelines use iterators. They are pulled by iterator, right, which is on the right-hand side. Push-based pipelines are pushed on the subscribers, right? So the left-hand side pushes on the right-hand side. In both the cases, not in both the cases actually, in pull-based, terminal action triggers the data flow, like for each or some sync basically. And that terminology is constant across, I think Java 8 streams also use terminal action. Spark calls it actions actually. And then there are two varieties: perishable, reusable. Those are the examples. Both of them could be memoized and then used multiple times, basically within a single consumption. But if they don't memoize, then reusable can be used multiple times without consumption. For push-based, they're hot and cold. Well, hot doesn't need a trigger to start. They're always started, mostly UI events. Cold is the subscription, the first or the whole graph creation, right? And then trigger will start it. They are most relevant for the IO-based programming, as you will see in the demo. And they can be back pressured. So if they are back pressured using the protocol that we saw, those are called reactive streams. Akka stream is one example of that. Okay, now I have some demos basically, but before I do start that, any questions? Demos will take 10 minutes. Any questions? Okay. So what the first demo is so we are trying to basically depict a video camera basically, right? I mean, so there is a source on the left hand side which is generating a lot of frames. It's like some telescope video camera which is generating a lot of frames. What we want to do is take these frames through multiple nodes on the system, right, across the network possibly. Right now it's all on my machine, but across the processes over HTTP actually, and then take it to one of the nodes which is say a browser, and then browser should have some way of rendering these images. So what I have done is taken a video of 10 minutes and spliced it into frames of very small sizes, and then I have used Akka HTTP basically to stream these frames over WebSocket. It will Akka HTTP itself will use file IO. It's a blocking file IO actually, but yeah, it has a separate thread pool. You can assume that in the latest in the new version of Akka, which works on Java 8, it will be completely non-blocking IO. And WebSocket on the client side, I use Scala.js. So we talked about a talk where people are talking of compile to JS. So I have used Scala.js basically as an example. And then browser actually does the rendering. So that rendering blocks, because rendering is an expensive operation, so that blocks. So there are two kinds of back pressure. So here on the left hand side, it is all async back pressure because it's using Akka streams. But on the right hand side, it is the trigger of the back pressure is synchronous because JavaScript is single threaded, and each render will not allow next message to arrive on WebSocket unless it has rendered. So let's do that. So what I'm going to do is I'm going to start my server, right? And then okay. So what I have done on the right hand side here, I have a console so that you can see the throughput. So I'll show you the code also, but first let's see. So these are the images which are and this is a throughput. So I'm getting like right now I got 36 images per second, right? So last second, how many images I'm getting? And this is actually this is not a video, right? There is no encoding, nothing. Just a plain images I'm rendering on the canvas, and I'm getting pretty good throughput, but that is not good enough actually. And the reason being that the browser, right? The bottleneck is the browser and the rendering. I'm going to do the same demo now without the UI between the two servers, and you will see the big difference. I mean, it's just order of magnitude faster. So right now your throughput is like what 30. Even if I just disable this, even if I just disable rendering, my throughput doesn't change a lot. I'll show you that. So let me just refresh this. So this one is a WebSocket. So this is the other project. Right. So this is the Scala code that I was talking about. and I have used RX reactive extension. So there is a multiple implementations of RX. The one in Scala.js which works in the browser is called as Monifu. So I have used that. So I'm doing a lot of things, make URL, blah blah blah, and finally the last line, this line actually computes the throughput, right? It says that okay, how many per second you are getting, and this is the beauty of the streams, any streams, whether reactive streams or UI streams, data streams, that you can do beautiful, very concise operations like this. I could just get a throughput in one logical line. I say buffer for 1 second, and then of that buffer compute the size and then just print on the console. So now what I'm going to do is I don't do anything, right? I just say that okay, get the events from the socket, web socket, and just see how fast, what is the throughput, right? So this should give us the raw throughput without any bottlenecks. So it will not render anything. Oops, why is it rendering? Okay, sorry, I did not restart. So this is that, and let me restart it. Okay, so throughput is doubled, but it's not very impressive, right? So right now I'm getting 46 without. So only operation I'm doing is a IO operation, printing on the console. There is no other and WebSocket, right? If I use whatever web workers and do some magic, right? I mean maybe I will, but this is really bad. I will show you in comparison, right? So if I let it run, maybe it will run for 5 minutes. The video real length of the video was 10 minutes, but this is slightly higher throughput, so it will run for 5 minutes or so. Okay, I'll just stop this now. So I'll say stop. Okay. Now what I'm going to do is a similar exercise, but with server to server. So which means that I have a source of files and I have a sink of files instead of browser. And I have two HTTP servers. One is guarding the source, one is guarding the sink. So one is serving the file, so I have a get call there. And on the other side, I have a post call, right? So two servers. And my test is basically not test. I have written a transfer agent which will get data in a streaming fashion from one source and keep pushing to the other source, right? Both the HTTP or Akka HTTP. Now, important thing to notice here, I haven't used WebSocket. I could, but Akka HTTP, the client-side WebSocket is not available, right? So I couldn't write this agent, but it should be available very soon. So I will see compare the performance. It could be the protocol itself, which is so WebSocket is considered to be very fast and efficient and all that. But right now, what I'm using is chunked HTTP get and post, and that is unbelievably fast. I mean, I don't see a big difference in why. So if you have to use streaming over HTTP, you can just use HTTP 1.1 and the chunked get and post. Right? So, well, and there is a async back pressure. I forgot the point, but async back pressure and all that. So, which means that if sync is really slow, it will slow down the post. So my disk is moving slowly. So my post will not receive the next chunk. Basically, it will not demand across the TCP network to my transfer agent, and the transfer agent will not demand the next chunk to Akka HTTP server, and then it will not demand to the file, and so I will not lose any data. Well, even in the previous demo, I did not lose any data. Here also, end to end, I will not lose any chunk of data. Right? So now I have two variations of this. One is with the same frames, 14,000 frames that we saw. So let's first run that one. One-to-one transfer frame objects. And then you can do the calculation later on, but there are 14,000 frames, and it approximately takes 30 seconds. So I think roughly 500, right? So this is like at least 5 times with the raw. Actually more than that, almost I would say 10 times order of magnitude faster than this. And this is going across processes, right? In fact, it is crossing 2 process boundaries. So one on that server and one that's going via my agent, right? Still very fast. Okay, 30 seconds done, including all the warm-up and stuff. So I need to measure, and we can see that later. But that is an interesting insight. Now, what I can do with the small images, each chunk is representing one image, because my image is very small, 100 around 100 KB. But what I can do is I can apply the same principle to transfer huge amount of large files, basically, right? And there I can do some more complications. So for example, I can do something like this. Now assume that my use cases changes slightly. So I have to demo you the multicasting, that I have to read things only once and then multicast it to two. So I split the pipeline into two. So my left hand side remains as it is, but my transfer agent now actually is posting to two syncs, right, via again HTTP. Now there are multiple process boundaries involved, right? Three HTTP servers you see, and my client, my transfer agent, and that all runs on my machine. That is also very efficient. Now I have movie files which are like around whatever half GB size, and I can control how many connections on the left and right and all that. So I will just go with the default, and I will do that demo. So one-to-many transfer test, right? Okay. So here what you will see, so I'm just dealing with four large images, right? Four large images, because by default, Akka HTTP has four connections on configured. So you see that they're read only once. All the movie files are read only once, but they're written twice, right? On those two streams. Now, they are not coming in memory like the frames of the small frames. Chunks, the file is broken into chunks, and one chunk is coming from the left hand side and being transmitted to the right post, but across the HTTP. And then this will take another 10 seconds, and then I'll show you the code. Okay, so this is done. Now, if you want to see the code, this is how my one-to-one transfer looks like. So I have a class which has just created a flow, basically. Now this is all about the Akka HTTP Akka stream DSL. I have a flow. I'm connecting two flow, the producing flow and the consuming flow. There is a one-to-one connection, so I just have to join them by a via operator. Each flow is basically interesting. So the first flow is taking a string, which is this, and giving me a message entity. Now, why I could implement it very, very concisely, because the message entity that I get from the response on the left hand side, I'm able to take that and directly put it in the request, the post request, right? And the entity itself captures the streaming aspect. If you explore, this code is pushed, so you explore the code and you will appreciate what I'm saying. So I take out, I generate this message entity, which is response.multicast entity, and then my consuming client directly takes that entity, which is here entity, and then puts it into a request, post request, that it is creating on the right hand side. In this case, just for one-to-one, but I can do the same thing for one-to-many transfer. Here, as you can expect, I will have a graph, but with a single trigger, because this is pure I/O operation. So I can create all my topology. This is simple, but I can go to basically I can really make a complicated topology of data transfer, and then decide when to trigger it. So here I create a same graph that I showed you earlier with the broadcast node and the merge node, and then that's but I reuse the producing client and the consuming client. The only thing is that the graph has to be created. It's not one to one. Right. So yeah, I think that's about the demos. Any questions? So how does library do that, right? So they implement this protocol that I was talking about. So back pressure is, well, the premise is that in a push-based system, there are two ways. Either you can say that, okay, don't give me more, and then push stops, right? The other way is that saying that give me some, and the guarantee is that I will not get more than some. And that is what the reactive stream protocol is. So that is what this request arrow is. So each downstream demands upstream that give me 10, and upstream respects that demand and doesn't push more than 10. And if this goes all the way up, So for example, Akka HTTP implements this protocol. So does RxJava latest version, and 2.x of RxJava will be completely based on this. And so does TCP. TCP doesn't implement reactive stream protocol, but TCP does the back pressure naturally. I mean that is inbuilt in the protocol. So you can anything which is going over TCP basically n number of hops, and they also follow reactive stream protocol. You get end-to-end back pressure.
This is assuming that your source is a cold source.
Yes. Right? Yes, it is. If it is a hot source, then you have to do something, drop, for example, or a fail, or you can convert a hot source into a cold source in an I/O system using tools like Kafka, for example. So Kafka is like, well, again, theoretically, you can say that, you know what, I have unlimited amount of buffer on my disk, which is Kafka, and then let all the hot sources come, and I will materialize I will serialize all of them on the Kafka, and theoretically, it is very fast. So I can serialize million events per second, but that is a limit. After that, if your Google Stream is giving you 2 million records, Kafka is not going to cope, so something somewhere has to be dropped, right? But Kafka is usually in the I/O setup. The kind of data streams that people receive, they convert. The reason Kafka comes into play is because roughly it is converting a hot source into cold source, because the downstream now can decide when to pull it, not immediately next minute, but maybe next day or next week, because it has enough infra basically to keep it for some time.
For this hybrid pipeline, will be able to set buffer as a fixed length buffer or unlimited buffer?
You can configure it. So now it depends on the libraries, right? So the protocol is really simple. It doesn't. It gives you a TCK basically, so that you can. So if you say,
This is similar to messages in Akka.
well, messages in Akka are kind of unbounded by nature, right? I mean, you can. It's a push-based system, yes, but it's a pure push-based. It's like the second line, second diagram. It doesn't have any back pressure inbuilt, unless you say that, okay, I have a bounded mailbox, and then after that it drops, right? It doesn't. Or if you want to create a back pressure, then you have to implement it in Akka actors or any actor system for that matter by yourself. What Akka streams do is that they use actors, but they do all this for you and give you a very nice collection like API on top. But internally, the stream is materialized on top of Akka actors. So reactive streams, GitHub, if you see. So you can, okay, they provide a TCK. So if you claim, for example, MongoDB has a driver for connection, which is now based on reactive streams. So which is really nice, because now I don't need to, I can make it Akka streams like this, because Akka streams provides connections with any driver which respects this API. So it has only 4 APIs: publisher, subscriber, subscription, processor, and then it has very few methods. For example, publisher has a single method. The next one will have 4 methods. So total 9 methods and all that. It doesn't specify that, okay, how much request you can send and how much buffer and all that. It's like up to the implementation of the library how configurable they want it to be. So Akka streams allows you a lot of configuration. It's pretty detailed actually. The documentation of Akka streams is also awesome. I mean, that is so Akka is very popular for good reasons, but I have never used it. But Akka streams, I will use it given an opportunity. It's like really awesome. Cool. Any other questions? If you want complete back pressure, basically, for example, usually in the UI style of programming, right, your subscribers will attach at any time and go anytime, right? That is different. Anyway, sources are hot, subscribers are dynamic. But in the UI pipelines, you know that your topology, you first design your topology, you say that, okay, this is how the data transfer is going to happen. So you have opportunity to trigger it at one point. What happens if you join late? Oh well, you lose data. I mean, that's okay. But in IO setup, I mean, that is a choice actually.
Will it be the transfer agent or will it be one of the subscribers?
Well, if you think in terms of my demo, it's a difficult question. But if you just think between a connection between a subscriber and the publisher, after you connect the subscriber in terms of Akka streams, you haven't triggered it. You just created a graph which is closed. So Akka streams has this notion of a graph, and if all the ports of that graph are closed, you can run that graph, and that running is a trigger. So if you have just one publisher, one subscriber, you connect it, your graph is closed. It's called as a runnable graph, and then you can run it. If you have a complex topology, you can build it, but ultimately you get a runnable graph that you trigger, and then the whole do. It's beautiful actually that the graph idea of Akka days is really nice. No, not in Akka streams. Not in Akka streams. You attach sinks, one, two, many, all that. You get a runnable graph. You appreciate it for 1 hour and then say run. And then it will trigger. Yeah. That's it. Thank you.
You're going to mention some other libraries.
So couple of libraries, for example, I compared with the IEnumerable C# collections. They are like they and Spark RDD. They belong to the reusable lazy pull-based systems, right? Scala iterator and Java streams, they belong to perishable pull-based iterators, right? Spark D streams, RX Java, Akka streams, they are push-based systems. Akka streams fully support reactive protocol. RX Java has started supporting it. 1.5 of a D stream, Spark D stream, will also have back pressure. Will that be based on the exact protocol or some other way? I don't know, but they are going to support that. Then I compared with the closure implementation, Scala streams and closure collections. What else? Yeah, I mean, those were the things I had in my mind.